Good morning, good afternoon, and good evening, depending on what time zone you are. Just for the sake of argument, we're spanning 16 time zones from Los Angeles, California to Seoul, Korea, as far north as state of Washington, as far south as South Africa. So we have quite a coverage here. Yesterday, roughly about 700 attendees between YouTube and Zoom. Let's give people a couple of minutes since I see the numbers creeping up rapidly here. If anybody has a question, you can put it on the chat and we can maybe address those. Last night, I sent a second batch of lecture notes. There might be a couple more, but the idea is to you have them, make sure you have them before the lectures. Okay, we've waited the canonical 5 minutes, so let's get started, or in some sense, continue with the presentation. Many of you asked if there was a charge for this course. There isn't. However, that doesn't mean it's free, meaning over the next few weeks or so, somebody will come ask for your help. Help that person out, consider that the cost of the course. Alrighty. So continuing on with our discussion, yesterday we began our discussion on the theory of electron transfer. And we mentioned that we would be focusing on Markov theory of electron transfer. We started by stating that there's two basic mechanisms of electron transfer, so-called inner sphere and outer sphere. Outer sphere can be considered a simple exchange of electrons between two spheres, meaning with coupling. Inner sphere involves a bridge between the reaction partners in the transition states and thus much higher degree of coupling. We described briefly in solution an outer sphere electron transfer between tris bipyryl ruthenium-3 and tris bipyryl iron-2. The ruthenium can oxidize the iron, and so the net electron transfer is from the iron to the ruthenium, as seen in the bottom. So you end up with ruthenium-2 and iron-3 as final products. And as we mentioned, the observed rate would be a product of a pre-association, this Ka, which is an equilibrium constant, and then the effective rate of electron transfer, Ket. On the other hand, an inner sphere electron transfer reaction is fundamentally very different from outer sphere in that it involves much closer coupling. In this particular case, this is a homogeneous solution reaction there's a very famous paper by Henry Tauby, and it was Tauby and Myers in 1950 something, a long time ago. But basically the idea that you start with hexachromium-2, which is a strongly reducing agent, and penamine chlorocobalt-3. The key here is that in the transition state, you have a bridge between the chromium and the cobalt, as exemplified here. And so that serves to bring the two reaction partners together. Then you can have electron transfer. Because of the changes in oxidation state, there's dramatic changes in the coordination environment. And so the end products here would be pentachlorochromium. And the important thing is that the chloride was transferred from the cobalt to the chromium, and then hexachlorocobalt-2 with basically all of the amines coming out. We mentioned that often, although it's not a requirement for inner sphere electron transfer reactions between inorganic reaction partners, there is often a significant change in coordination or geometry, but that's not a requirement. The requirement here for inner sphere is that there be a bridge between reaction partners, in this case provided by the bridging ligand, the chloride. And then we mentioned sort of analogous systems in electrochemical reactions. So for example, the reaction here of mediated by chloride, or in this case, tetraiodocadmium. And we also mentioned the fact that when thinking about, let's say, outer sphere, where we think of reactions between basically two spheres, that one needs to also significantly consider the solvent polarization, in particular because a 2+ ion will polarize the environment much less than a 3+ ion, and that's exemplified here by how ordered this little arrows that represent the dipole moment in the solvent. And the point here is that, once again, because of Frank Condon, there can be no changes in nuclear coordinates in the time frame of the electron transfer. And so because metal-ligand bond distances can be significantly different between a 2+ and a 3+ ion, then in the transition state, the 2+ ion has to shrink just a little bit, the 3+ has to increase a little bit, so that effectively they'll look like a 2.5 in the transition state, then the electron transfer can take place. So that's roughly where we stopped last time. So now we're putting all of this together in potential energy diagrams. And so here we have the reactants and product potential energy surfaces. Two things to notice. One, so if you the reactant, so there's a splitting here, and then the products. For electron transfer to take place, you have to go from the reactants to the products potential energy surface. If there was no interaction between those two parabolas, right, they would cross. And then if there's no interaction, there is no way for the system to go from reactants to products, because there's a nodal plane of electron density. You basically cannot move across that. By first order perturbation theory, you let these two parabolas or potential energy surfaces interact, and that creates a gap. The magnitude of the gap is called 2 beta in terms of energy, or HAB in some cases, which is the off-diagonal element in for the process. And what you want is for that energy to be big enough so you can actually get some splitting, but small enough that you can still consider the system as uncoupled oscillators. And this will become very evident in a couple of minutes. The way this is presented here, so you have A represents the equilibrium nuclear coordinates of the reactants, C represents the equilibrium nuclear coordinates of the products, and B represents the nuclear coordinates in the transition state or the intersection region. Notice that as plotted here, there is no net change in free energy. So this is basically the same. This would be for a quote unquote self-exchange process where you have the same, let's say, iron 3 plus iron 2. Of course, these are all hexaco in equilibrium with iron 2 plus iron 3. We can label this one we can tell them apart, but basically, there is no net free energy change in this process. So now we get to Marcus theory. We will consider the classical theory, meaning that we will only very, very briefly mention quantum mechanical tunneling, but the vast majority of the discussion will be based on the classical theory, for which he was awarded the Nobel Prize in 1992. So what does Marcus say, and what are some of the assumptions, and what are the consequences? So it starts, the microscopic configurations from a system may undergo, the microscopic configuration from which a system may undergo reaction, that is electron transfer, I assume to be in thermal equilibrium with the remaining states, meaning this is an activated process, right? If it's a thermal equilibrium, that means that the system must gain energy from the thermal pool to go up into the transition state or the intersection region in order for there to be electron transfer. And it says the electronic interactions are sufficiently large to allow for electron transfer. That means enough to basically split the two parabolas here, right? But small enough so that the potential energy surfaces are essentially those for zero electronic interaction, meaning it's big enough so you split the levels, small enough that you can still consider these as uncoupled oscillators, so it's a lot easier to treat. So what are the consequences? It says the electronic configuration and thus the charge distribution of the activated complex, that is in the transition state, is extremely sensitive to the nuclear coordination of the medium as well as that of the reactants. No kidding, right? I mean, that's exactly what the transition state means, that you have a system that is very sensitive to the nuclear coordination, the nuclear coordinates in the system as well as that of the reactants. And then during the course of a reactive encounter, the configurations or the nuclear coordinates of the system gradually, meaning it's an activated process, change from those characteristic of the reactants to those characteristic of the products. Meaning, if we go back to this idea of a 3+ and a 2+ sphere, the 2+ sphere has to get a little bit smaller, the 3+ sphere has to get a little bit larger. This is as a result of oscillations within the system, in essence, through the thermal pull, which is the environment. And so when it reaches configurations that are equivalent to those of the transition state, meaning intermediate between those two, then the electron can transfer. So it's another way of stating the Frank Condon principle, meaning that there can be no change in nuclear coordinates in the time frame of the electron transfer. Remember, so a change in the nuclear coordinate typically means some vibration. The typical vibrational lifetimes is in the picosecond regime. Electron transfer change in the femtosecond regime. So it's 3 orders of magnitude faster, and thus in that time frame, the nuclear coordinates are essentially frozen or fixed. And then finally, it says the configurations that minimize the free energy of formation, meaning that minimize the free energy of activation of the activated complex, will contribute most of the rate. Again, this should be sort of self-evident, meaning if you have more than one pathway, the pathway that minimizes the energy of activation will be the dominant pathway. And that's just basically fundamental kinetics. So where does that take us? So he writes an expression for the rate, K, in terms of kappa, which is a transmission coefficient. As we'll see, this will go from 0 to 1. A sigma squared is a dimensionless collision frequency. Then you have an exponential delta G star, the free energy of activation, which can be further divided into work terms, the inherent energy of activation, and then which is further, this delta G0 prime is a delta G0, which is the free energy of activation. These are work terms for the products and reactants. So there's a lot of stuff in here. We'll go through this slowly. Excuse me a second. So if we go into, what is this? There we go. And so delta G0, the standard free energy of the reaction in the prevailing medium. And so the prevailing medium basically implies, what is this? Whatever the environment might be. And so I had to take into account everything that you have in the system. Free energy of reaction when the reactants are a distance r apart in the prevailing medium. And this will become very important. That's because you have the two spheres coming together. There will be a distance between them. And so it's a free energy of the reaction at that distance. And we'll see how that comes about in a second. W's are work terms, so work terms for the reactants and products. This is particularly the case if you have charged reactants. If you have a positive and a charge, a positively and a negative charge reactant, then that work term favors you. If you have equal charge, say plus, both positively charged or both negatively charged, it will be repulsive. And so it's the net difference between those terms that will be appropriate here or relevant. An interesting point here is that if you want to eliminate, complications due to work terms, if one of your redox couples is neutral, then you basically dispense with that. And that's one of the reasons, for example, why ferrocene is such a popular couple. It not only is a very fast redox couple, but essentially the work terms are zero because you go from ferrocene, which is neutral, to ferricenium, which is positively charged, but then the work terms are zero because it's an interaction between a positively charged species and a neutral species. This is in the conversion from iron 2 in ferrocene to iron 3 in ferricenium. Lambda is a reorganizational energy term that is further subdivided into lambda inner and lambda outer. Lambda inner takes into account changes in metal ligand bond distances and polarization. Lambda outer takes into account polarization of the solvent, and we'll delve into that in much deeper form. Kappa is an interesting parameter. And so kappa of R, it says transmission coefficient or average transition probability for electron transfer per passage to the system of intersection region at a fixed separation distance R between the two reactants. That is one hell of a mouthful. What do we mean by that? So it basically tells you the transmission coefficient for, or basically what's the probability of electron transfer in some sense. If you're very far apart, that probability is low because there's very little overlap. As you get closer, it gets better. And so this kappa takes into account, it averages what that transition probability is at a given distance R. And it says at large R, kappa of R is assumed to vary exponentially e to the minus beta R. This has been shown experimentally by looking at electron transfer in cases where you have a surface and you have a redox couple tethered to the surface, and you can basically vary the distance R. And it's basically one order of magnitude per angstrom. So it's extremely sensitive to R when you are close to the electrode surface. And then when you average kappa over R, then we basically denote it by kappa. For an adiabatic reaction, means one that always stays in thermal equilibrium, kappa goes to 1. And we have a lot more to say about that again in a second. And so this idea or this concept of adiabaticity of electron transfer generates a little bit of anxiety and some misunderstandings. So the adiabaticity, it says, refers to the probability of the electron transfer once the system is in the intersection region. Okay, so what are we saying? Remember, we have these two parabolas, right? At the intersection region, the question is, if I'm at the intersection region, what is the probability that I will be able to have electron exchange? Notice that for adiabatic reactions, we said that kappa equals 1 or goes to 1. Now, what does the probability depend on? It depends on the rate of oscillation between the two equivalent sites, the length of time it spends in the intersection region. What do we mean by that? So the easiest case to consider, imagine a self-exchange rate, right? So that these are two identical parabolas. The only difference is where does the electron lie, but there's no driving force in terms of the thermodynamic driving force. We are basically at equilibrium. Yet remember that these are dynamic processes. There's still electron exchange at the self-exchange rate. And so then let's say we get to the intersection region, right? If I'm looking down to the left and to the right, they look identical to me. If they look identical to me, my gut feeling would be that the probability should be a half, because half the time I am in one place and the other half I am on the other place. But that is not what this says. This says that kappa goes to 1. So how can that be? And this is where the length of time descent in the intersection region comes in. What this basically tells you, right, is that the length of time in a system spent in the intersection region, that will basically correspond essentially to a vibrational lifetime, because that's the time you have for things, electrons to move without having a change in the nuclear coordinate. And so the question really is, in the time frame of a vibration, let's say for good measure, say 10, 20 picoseconds, did that electron sample the product's potential energy surface? And if kappa equals 1, then the answer is yes. Where the electron ends up, it's basically irrelevant in this context. What's important is that electron was transferred, but because it can exchange very rapidly, then it can do this many times in the time frame of the transition state, basically these 20 or so picoseconds. This comes about from the so-called Landau-Zener equation in terms of the thermal velocity with which the intersection region is approached. And what that means is that if you think of the two parabolas, then the thermal pull basically is sloshing those things around. The speed at which the species approach the intersection region has a lot to do with it. If it's low enough so it's always in thermal equilibrium, you maintain thermal equilibrium, the process is adiabatic. If it gets too, let's say, enthusiastic, it can actually jump the gap and stay on the reactant surfaces, and then that event is not successful in terms of electron transfer. If you ever have any trouble falling asleep, I recommend this article intensely. It is essentially impenetrable, but it's really very useful. The conclusions are really very good. It has like 5 lines of text and everything else is math. And so, as we mentioned, if heat equilibrium is lost, right, and it's lost because you're approaching the intersection region too fast, then the process system non-adiabatic and kappa will be much less than 1. If you maintain heat equilibrium, the system or the process system adiabatic, and therefore kappa equals 1. So in summary, the idea of kappa going to 1 in an adiabatic system means that in the time frame where the system finds itself in the intersection region, that electron sampled the potential energy surface of the reactants at least once, and more than likely many times in the time frame of that. Remember, we're talking about 3 orders of magnitude difference in the relative time frames of electron transfer in the femtosecond and vibrational lifetimes in picoseconds. So how does this modify our view of things here? So we go back to the same expression. So we basically covered transmission coefficient just in the last couple of slides. The A sigma square refers to the dimensionless collisional frequency. Actually, if you think about this, so let's say kappa equals 1, this is basically the pre-exponential in an Arrhenius type of expression. And so what you have is a constant, which is k. Let's say if it's adiabatic, that's 1. So you have the k equals pre-exponential exponential with activation energy over RT. That is basically a first cousin of an Arrhenius type expression. It's mathematically identical, and that's why this basically follows the same formalism. And so here's a dimensionless collision frequency. As we mentioned, delta G star is a free energy of activation that takes into account work terms, the reorganizational energy term, and we'll have a lot more to say about this in a second. The other thing is at delta G zero prime, which is the free energy at a distance r in the prevailing meter. Now you can see why r is so important, because it's not just the free energy change. It's a free energy change at a specific location at which electron transfer can take place, and particularly a distance r apart. Again, work terms for reactants and products. The reorganizational energy term, lambda inner and lambda outer. So if we delve a little bit more deeply into these terms of the reorganizational energy term, by the way, the idea of casting this in terms of the reorganizational energy term is probably one of the most fundamental and one of the most important aspects of Marcus theory, because these are things that we can either measure or at least calculate reasonably. And so it provides a means for predicting what the rate of electron transfer would be. And that's the enormous power of Marcus theory. And so we can look at lambda inner. So lambda inner says the lambda inner sphere reorganizational energy term. It refers to contributions due to bond length differences between reactants and products. So if you're looking at a transition metal complex, what is the metal ligand bond distance as a function of oxidation state? If you have a very polar ligand and a 2+ or a 3+ ion, then that metal ligand bond distance will be very different in a 3+ than to a 2+. If that's the case, then remembering that in order to get electron transfer, we have to have nuclear coordinates that are intermediate between those of reactants and products. That means that in the 3+, you have to stretch that bond. In the 2+, you have to compress that bond. That spring constant and the distance, the delta R, will basically determine what the lambda inner will be. Lambda outer, as we mentioned, is the outer sphere reorganizational energy term, and it refers to the contribution due to differences in the solvent orientation or polarization between reactants and products. And this goes back to this idea of the spheres and having the little arrows representing the dipole moment of the solvent. In a 3+, those things are polarized much more than in a 2+, let's say. So if we look at lambda inner, so inner sphere reorganizational energy term, it can be cast by this expression. And what does that mean? I mean, it's a lot simpler than it looks. It tells you that the lambda inner is a sum, so you have sigma, over normal modes, and normal modes meaning the vibrations, that basically are relevant in the electron transfer event. And so it includes the normal modes, and it includes the force constants for reactants and products. So F of R is the force constant for the reactant for mode J. F of P, so this is a force constant for products for mode J. So it's a product divided by the sum. Delta Q is the difference in the metal ligand bond distance for mode J at different oxidation states. And what the hell does all that mean? So if we go back to our example of hexaco iron 2 or 3, this delta Q is the difference between the iron and the oxygen in the 3+ or the 2+. The bigger that difference, the bigger lambda inner is. And notice it's the square of that. And that's because it's basically you're thinking of a harmonic oscillator. So delta Q, it's, kx squared, in the harmonic oscillator. And that basically determines the energy. In this case, the lambda inner, that energy is reflected in the lambda inner. So again, it'll be a summation over the various normal modes. So here's where the J index comes in. And we take into account the force constants for the reactants. So the reactants for mode J, for the products at mode J, the product divided by the sums, and then delta Q. And so here again, these are force constants for the Jth mode. Delta Q is a change in the equilibrium value of the Jth normal coordinate as a function of oxidation state. let's go back here. So if I look at this expression, one of the things that I would like to do is minimize delta Q, because a large delta Q means that lambda inner is large, my rate is going to suffer. And the easiest way to do that, for example, if you have octahedral coordination on a metal center, instead of using monodentate ligands, use chelating ligands. Because of the chelate effect, that metal ligand bond distance usually is much smaller than in simple monodentate ligands. And in fact, there's great evidence, in support of this. For example, if you have a metal complex with, 6 amines, so hexamine and your favorite metal, as opposed to ethylene diamine, so 3 ethylene diamines, so you have a chelate. In terms of coordination strength, they're very, very similar. In terms of the geometry, they're very different. And the rate of the tris ethylene diamine complex will almost always be faster than the hexamine. And so this is a simple case where by controlling the geometry and the binding type, you can really have a dramatic effect on the rate of electron transfer, because you're in essence mitigating or making smaller this delta Q between oxidation states. For lambda outer, so here we have lambda outer is delta E, where delta E is the charge transferred, squared, notice, squared. And then A1 and A2 are the radii of the reactants. 1 over R is the center-to-center distance. And then you have the optical and static dielectric constants. And so this is, in essence, very similar to the Born expression for polarizing a sphere. Let's go through these terms one at a time. So clearly, the radii of the reactants makes a difference, right? Because if you have a reactant that looks like that and a reactant that looks like that, you still have to go from here to there. And the R is basically that. So this would be, let's say, A1. This would be A2. And then this distance would be R. And that's just basically a geometric factor. D up and D static. So the D up is basically the square of the dielectric constant, or the static dielectric constant. I mean, the DS, and D up is the optical dielectric constant. And why the dielectric constants? Because it's the only thing that can react fast enough in the time frame of the electron moving. As the electron moves, it can sort of polarize that charge distribution while maintaining a fixed nuclear coordinate. And so if I look at this expression, right? So I mean, these are basically constant, dependent only on the solvent. And these are basically depending on your reactants and the distance between them. What if we look at this delta E? If I look at that and I say, can there ever be multiple electron transfers? All right, it's delta E squared. So if I do a 1 electron transfer, 1 squared is 1, we're good. If I do a 2 electron transfer, I can do 1 squared plus 1 squared, and that's 2. If I do, 2 squared, that's 4. So everything else being the same, why would I ever have a 2 electron transfer? I pay an enormous penalty. And yet there are processes that transfer 2 or even more electrons. And so the question is, how can that happen? And so we go back to this idea of time frames and timescales. What we're saying for a 2 electron transfer is that in the time frame of the system, you see, in the intersection region, you can transfer more than 1 electron, but more than likely 1 at a time. And in that case, you don't, violate anything here because you're transferring the electrons while the system is still on fixed nuclear coordinates, but you're not doing them two at a time because that's just too expensive energetically. And so in essence, this tells us that virtually all multi-electron transfer events basically take place one electron at a time, except that you have to transfer those electrons in the time frame of the transition state. And that's where that comes from. Now, one of the more powerful things of Marcus theory is the so-called Marcus cross relation. And what that means is that if you have a tabulation of self-exchange rate constants, meaning both red and ox are the same. So this would be self-exchange for process one. This would be self-exchange for process two. If you look at both sides, so you have red one, ox one, red two. Basically the same thing. It's just that red get converted to ox get converted to red. No net change. And then you can have the same for the process number two. And so what Marcus cross relation says is that if you have a tabulation, if you have a list of constants for self-exchange, you can then mix and match those values to obtain what the mix rate would be. That is red one and ox two going to ox one and red two, which is basically a combination of the first two reactions. In this case, the K individual Ks are quote unquote word corrected, meaning if you have charge intermediate, you need to do some corrections, which are relatively straightforward. It's just electrostatics interactions. That being the case, then the Marcus cross relation states that K12, the mix rate, this process, is equal to the product of the self-exchange rates, a pre-equilibrium, K12, meaning remember this pre-association, which you can actually get spectrophotometrically, and then this factor F12 that basically works out. It's a rather complicated expression here. In practice, when it's all said and done, it turns out to be not much different from one. And so basically what we have is this we know, this we know, this we can measure. If we say that this is one, then we're really in very good shape. Meaning, if we have reasonable values for self-exchange rates, we can actually calculate what the mix rate or the cross relation or cross reaction would be. What's implicit also in this formalism is that the mixed reorganizational energy term is basically the average of those two. If their two systems have very different lambdas, then this approximation will break down and you'll get into trouble. Nevertheless, it's a very simple relation, and as we'll see in a second, it has amazing predictive value. And so this is one of the biggest aspects as to why Marcus theory got to be so popular, because it enabled you to predict what rates would be. And at the time, and we're talking about the 1950s when this first came out, there was nothing close to that. And so here's a comparison of calculated and experimentally measured K12 values. And so if we look, so here we have on the top one, hexachloroiridate and octacyano tungstate. The observed rate is 6.1 times 10 to the 7, the calculated one, 6.1 times 10 to the 7. That is ridiculously good and more than likely accidental, but it's very good. If we go to hexachloroiridate and ferrocyanide, let's say 4 times 10 to the 5th, 7 times 10 to the 5th, which is also very good. So in this game, if you're within an order of magnitude, that's considered amazingly good correlation. But then there are certain cases where things look a little bit off. And in particular, let's say something like this. It's cobalt bis-terpy, cobalt 2, and hexaqua cobalt 3. The measure is 7 times to the 4, the calculated 10 to the 10th. So a mile 6 orders of magnitude off. That by any metric is a horrible result. Okay. Why is that? And so remember that the assumption in this treatment is that you have simple electron transfers between reacting partners. There's a question, I'll get to that in a second. Let me just finish this. If you look at the coordination hexaqua cobalt 3, cobalt 3, cobalt 2 with hexaqua, basically you can have spin exchange, meaning it can be high spin in one oxidation state, low spin on the other one. And so in this particular case, cobalt 3 will be low spin, cobalt 2 will be high spin. And because of this reaction, even though it's a simple 1 electron transfer, there are a lot of moving parts here. You basically have like 4 electrons moving, and that's just very, very slow. And so even though the calculated value is 10 to the 10th, the actual value is 10 to the 4th. So whenever you have a system that can have high and low spins in different oxidation states, be extremely, extremely careful, because you're more than likely to be wrong. Okay. And that's particularly the case for cobalt with low ligand fields with low ligand field strength. Remember, the high spin and low spin, you're comparing the pairing energy versus a crystal field stabilization energy. If you pair the electrons, there's repulsion, but if you put them on a higher level, then you're basically missing that crystal field stabilization energy. And the balance between those two is whether you have a high spin or low spin. So there's a question here, can you please explain why K equals 1 when the electron can exchange rapidly between both parabolas? Because if it makes it across, that's an electron transfer. And so remember that K equals 1 basically means an adiabatic process, meaning that the electron gets transferred from reactants to products. And so the idea is it's not where the electron ends up, but the fact that the electron sample the product's potential energy surface, at least one in the time frame of the transition state. Okay, let's continue with our discussion here. So I mean, there's now a lot of tabulations, you know, and as I mentioned, some of them are reasonably good, some of them not so good, and very often in systems that can have a difference in spin exchange. Let's go back to free energies of activation and what ends up being an incredibly counterintuitive prediction that was born by experiment. So if we look at delta G star, right, the free energy change activation, we had work terms, lambda, and then this quadratic term. So we have the reorganizational energy term, and then this 1 plus delta G0 star over lambda quantity square. If we assume that work terms are negligible, just to dispense with this, right? So we end up that delta G star equals lambda over 4, 1 plus delta G star lambda quantity square. We can identify 2 regions, a normal region and a quote unquote inverted region. And what do we mean by that? When lambda is bigger than minus delta G, this is called the normal region, meaning that the rate increases as delta G0 gets increasingly negative or less positive, if you will, meaning the more favorable the process, the faster it gets, right? When delta G 0 prime equals 0, right? If this goes to 0, then delta G star is lambda over 4. This is called the intrinsic energy barrier to electron transfer. When delta G gets bigger than lambda, what happens here? So minus delta G, right? You have minus delta G over lambda, because you square this. When you square a negative number, it becomes positive. And so now you have the very unusual situation that the more favorable, meaning the bigger the minus delta G gets, the slower the process gets, because this activation energy is going up. And that is incredibly counterintuitive. It's basically saying that the harder you push, the slower it gets. And that's why it's called the inverted region, meaning the process decreases as the driving force increases. And we basically have no, in our physical world, we have no equivalent experience with that. When you push, when you throw a bowling ball down the alley, the harder you push, the faster it goes. Imagine you have the Hulk doing that and he throws with all its strength and the ball just barely moves. That's simply just very, very counterintuitive. And so how does this arise? And so here is one of the more famous diagrams from Marcus theory. So what we're presenting here, log K versus delta G. When delta G is bigger than minus lambda, meaning the reorganizational energy term, is basically an activation process. So you have to go from one to the other. When delta G star equals 0, you basically at the bottom of this, so you can basically go, if you're here, you just basically go down. In this regime, as you make delta G more negative, and you basically climb up this parabola. Eventually, you hit sort of a maximum, but then things really get funny when you go to very, very negative delta Gs. And as you can see here, even though the process is really downhill, I mean, it's down that way, you still have to go up here to get down. This comes about, what we're basically doing is nesting these potential energy surfaces. And so in this regime, you can see that even though the system is really downhill, it takes an activation energy to overcome that barrier, because now you have nested those two potential energy surfaces. Meaning the more favorable, the slower it gets. And that is just counterintuitive. But call now, like 1-800, we got the data. And so this was a series of experiments. We have, these are measured values. So these are experimental values. All of these. And so what this was, there's some constraints that you need to put in here, and that is you want to change only the driving force of the electron transfer event. You want to keep essentially lambdas as constant as possible and keep the distance as constant as possible. So you have this very rigid framework. You have a donor and you have different acceptors. And by changing essentially the redox potentials of different acceptors, then you can basically change the nature of the driving force. And so it doesn't take much to basically put a parabola around that. And that is experimental verification of the inverted energy region. Once this was published, basically everybody started the clock saying, how long before Rudy Marcos get the Nobel Prize? It was basically a couple of years. This is just such a counterintuitive prediction that works out that it's to me still one of the most astonishing conceptual developments in electron transfer. A couple of things. Can the inverted region be observed for electrode reactions? And for metal electrodes, the answer is a resounding no. Why is that? Because in a metal, you have a continuum of states, right? Which you can describe as a Fermi-Dirac weighted distribution. This can only take place when you have discrete redox levels. So you either jump or you don't jump, but you can't do it sequentially. This is also present in so-called, in photochemistry, the energy gap theorem, where the fluorescence quantum yield increases as you increase the gap between donor and acceptor, or from excited state to the ground state. In essence, that reflects, because if you have a photoprocess, you have basically a big chunk of energy that you're disposing. You can dissipate that by emitting a photon, or you can deactivate vibrationally. But when the energy gets so big, there is no vibration that can effectively dissipate that energy. So rather than thermally, so down conversion to the ground state, it basically emits a photon, and thus the quantum yield increases as the distance or as the energy gap between excited state and ground state increases, the so-called energy gap theorem. At semiconductor electrodes, you can do that because you basically have band gap. And so you can have inverted region in the case of semiconductor electrodes. So this finishes our discussion of electron transfer. It's almost up to the hour. Let's take 3 minutes so everybody can get a biological stop, and we'll reconvene at 10 o'clock. So back in 5. And we're back. I wanted to very briefly go back to the question of as to, kappa equal 1. So if we go back to the potential energy surfaces, right? So we had something like this, right? Where this is reactants and reactants, products and products. The idea of this velocity of approach, meaning as you approach the intersection region, if you're going too fast and you lose thermal equilibrium, you basically jump and stay on the reactant side. If you maintain thermal equilibrium, then you can basically stay here and then sample the products, potential energy surfaces. Hopefully that will be enough of an explanation here. So the next subject is double layer. And so this is probably the most, in terms of double layers, the most cited and probably least read article is called The Electrical Double Layer and the Theory of Electrocapillarity by David C. Graham at Amherst College in Amherst. You may not be able to read the small print there. And so there it is. And it says, original manuscript received July 24th, 1949, duplicate manuscript received July 14th, 1947. And you might say, what the hell does that mean? It means that the original, I mean, this is in the 40s, so this is just mail, right? I mean, no E of anything. It's just, typed manuscripts. So the initial manuscript was lost in the mail. So they had to submit a duplicate one that arrived in 1947. The original arrived 2 years later, 1949. So imagine that as you submit your most recent work to JAX, where if it takes more than a millisecond, you're concerned, imagine waiting 2 years for your work to be even received by the journal, much less published. And so it's a very interesting happening here. And so David Graham basically did absolutely one of those beautiful pieces of work that were experimentally very simple. And basically the measurements on all of this double-layer structure entailed the use of a dropping mercury electrode. For those of you who are not familiar, in a dropping mercury electrode, you have a very thin capillary, and then basically mercury drops that fall in your electrochemical cell. And the rate at which they drop is a function of the applied potential, and that's the term electrocapillarity. And so what he had a bunch of undergrads with stopwatches, basically counting how many drops would fall as a function of time for a whole range of experimental conditions. That served as a basis for a lot of the theory of the electrical double layer. So great credit to David Graham and this army of undergraduates at Amherst College. Notice, this is 1947. This is a long, long time ago. So what do we mean here by double layer? It says the interface between an electrode and an electrolyte solution are properties associated with the fact that if we apply a potential to the electrode, ions can be attracted to or repelled from the electrode surface due to electrostatic effects. And that should come as no surprise, right? If I have a surface, I put a charge. If it's a positive charge, anions will come in to screen that charge. If it's a negative charge, cations will come in to screen the charge. Remember that if we have a metal, the charges on a metal are literally on the surface, right? You cannot sustain an internal electric field in a metal. And so when you say on the surface, it's on the surface. And so you have a layer of charge at the electrode surface. You have a solution that will react so as to screen that charge. So what are the consequences of this? So it says the electrode solution interface has the electrical properties of a capacitor known as a double layer. For those of you who are not familiar with electronics, that's a capacitor, right? And so every time we change the potentials of the electrode, we have to charge or discharge the capacitor to accommodate the new applied potential. What does that mean in practice? That before you do any electron transfer, your electrical double layer has to relax to whatever potential you applied, so that you can actually do the process that you're interested in doing. So for a capacitor, the current is the capacitance times dE dt, meaning change in voltage with time. For double layer, so now the double layer current is a double layer capacitance, again, dE dt. But, the capacitors, if you go and to a store and buy a capacitor, it'll tell you, so many microfarads at a given voltage, and it's fixed. For the electrical double layer, the capacitance is a function of ionic strength. Capacitance is a function of applied potential. So in that context, it's a very unusual capacitor because its capacitance will be dependent on ionic strength and applied potential. And so any, and I mean any theory of the electrical double layer has to account for these dependencies because they are experimentally observed. Okay, as Isaac Mauritius Kolthoff, one of the greatest analytical chemists of all time from University of Minnesota, he said, theory guides, but experiment decides, right? And so any theory has to basically predict or explain dependency on the applied potential, dependency on the ionic strength. So if we have an electrode in contact with an electrolyte solution of non-adsorbing, right? We've already discussed what a non-adsorbing electrolyte is, meaning one that only responds to electrostatic fields. And we apply a potential that is negative relative to the solution, right? If we have a net negative charge on the surface, then cations will be attracted to the interface and anions will be repelled. That should come as no surprise, right? If my surface is negative, I need cations to screen the charge, and I will repel anions because I have a negative surface charge. And so when the potential of the electrode is negative to that of the solution, the surface concentration of cations is higher than in the bulk because I'm concentrating it to screen the charge on the electrode. And conversely, the concentration of anions on the surface will be less than in the bulk because I'm repelling those. And these differences are often referred to as quote unquote surface excesses. And a surface excess can be positive or negative. And in this case, the cations have a positive surface excess and the anions have a negative surface excess. And very often we use a symbol gamma for surface excess, which you might recall is the same term we use when talking about surface coverage when we're talking about adsorption. And so the opposite will clearly hold when we are potentials positive relative to solution, right? And so the surface concentration of cations will be less than the bulk. The surface concentration anion will be bigger than the bulk. And so this seems very reasonable. We did a real sleight of hand here, because if we went from a surface that was negatively charged to one that was positively charged, somewhere in there, we must have gone through a potential where the surface was electrically neutral, right? So there's the above variations imply that at some potential, the electrode will be neutral relative to the solution. That is, the electrode will be electrically neutral. And this is a really important concept known as a point of zero charge or the potential zero charge, EPZZ. And this is of truly fundamental importance. This is so because it tells you on a potential scale whether your electrode is positively or negatively charged if you know what the point of zero charge is. And what could be more important than knowing the sign and the magnitude of the charge at your electrode surface, right? And thus clearly of enormous fundamental importance in electrochemistry. If we look, so this is actually, these are data from that article that we just mentioned. So these are potentials of zero charge in various electrolytes. So we have sodium fluoride, sodium chloride, potassium bromide, potassium iodide at different concentrations from 1 millimolar to 1 molar. For sodium fluoride, 0.482, 0.48, 0.72, a very small difference here of about 10 millivolts. And we can actually explain that by just differences in the ionic strength. Sodium chloride, now we're talking about 50 millivolts. Potassium bromide, we're talking now 110 millivolts. Potassium iodide, 250 millivolts. So small, noticeable, large, enormous. Right? What does that mean? Remember, the point of zero charge is the potential at which the surface is neutral. If I increase the concentration of the salt or the electrolyte, and the point of zero charge changes, and in this case, more negative, that tells me, if you think, when you change the concentration, in some sense, it is like, remember, it's like an isotherm, right? So you have, let's say, surface coverage, solution activity, right? As you add more, you get more coverage on the surface. If you're getting more stuff on the surface and it's negative, that means that you have to apply a more negative potential to displace them. That means that if the point of zero charge moves negative with an increasing in concentration, you have specific adsorption. And not surprisingly, iodide very strongly specifically adsorbed, bigger than bromide, bigger than chloride, essentially irrelevant in the case of sodium fluoride. And this changes in the point of zero charge with concentration is known as the Ising-Markov effect. It's also very relevant in biological systems when you have membranes and membrane potentials. So if we look at the distribution of species at the interface for different electrolytes and at different potentials. We use one-to-one electrolytes. And we do that because the math is a lot easier, okay? So either, let's say, potassium chloride, sodium fluoride, etc. You would not use, potassium phosphate because it's just a colossal pain in the ass to calculate what the relevant species are. In any case, let's say we have sodium fluoride. It's a one-to-one electrolyte that is non-adsorbing, okay? And remember, our quintessential non-adsorbing is something like sodium fluoride. And so here's the electrode surface. We'll typically have a layer of solvent in intimate contact with the electrode surface. Because we are positive of the point of zero charge, we need to screen that charge with an excess of anions. So if I count how many cations and anions, so here's one positive, two positives, I have 1, 2, 3 negatives. So I have the equivalent of one negative charge anion extra. And then if I go further out, I have 2 positive and another 3 negatives. So I have an excess of negative charge, which I need to in order to screen the charge at the electrode surface. Now, if I think of the size of the solvated anions, which is this species here, right, with its solvation sphere. If I imagine drawing a plane through the center of those ions, so those ions will contact the electrode through the solvation spheres as well as the solvation on the electrode surface. And that plane is known as the quote-unquote outer Helmholtz plane. Whoops. Or OHP. And that is considered the plane of electron transfer for non-adsorbing species. How far is that? Well, it depends on the size of the ion, right? But if we assume solvent molecule about 3 angstroms, so say 6, less than a nanometer for sure. Beyond that, you have a so-called diffuse double layer. So this is a region where there's an imbalance between the positive and negative ions, in essence, to compensate for the surface charge on the electrode surface. Beyond that, then you have bulk solution, meaning the solution doesn't know and doesn't care that there's an electrode with a charge all the way there in the left. We can look at distributions of ions and potential profiles. So if we look at the concentration, species, be it anions or cations, as a function of distance, so this is basically this point here. And then this region involves both the outer Helmholtz plane as well as the diffuse double layer, where you see a difference in the concentration. Cations are being repelled, anions are being attracted. Notice that I deliberately made the anion bigger than the cation because the electron cloud is going to be a bit bigger. If we look at the potential profile at that interface, here's the applied potential. It'll drop linearly to the outer Helmholtz plane and then exponentially out into solution. The potential at the outer Helmholtz plane is called phi2, and this comes from the nomenclature of Graham. Notice that we're using the solid state physics nomenclature here, or formalism. So negative going up, positive going down. So what happens if we reverse the polarity? So we have a non-absorbing electrolyte, a potential negative of the point of zero charge. So non-absorbing one-to-one electrolyte, potential negative of the point of zero charge. And so in this case, we have 3 positive charges and 2 negatives. So we have an excess of positive charges close to the electrode and excess of positive charge in the diffuse double layer. Again, because now we're screening a surface that is net negative. As we did before, we can draw a line through the center of the cations in contact with the surface through the solvation spheres. We call that the outer Helmholtz plane. In principle, the outer Helmholtz plane is different for the cations than for the anions. In general, we assume that they're the same unless there's some dramatic differences in size. It just makes things a little bit easier. So again, we have the outer Helmholtz plane, diffuse double layer, bulk solution. I'll get to the question in a second. And so if we look, non-absorbing one-to-one, negative of point of zero charge. Again, bulk solution. Now things are reversed. We have an excess cations close, depletion of anions. Now the potential negative goes to the other Helmholtz plane, again phi2, linear exponential out into solution. What happens when we put an absorbing electrolyte? So here we have an absorbing one-to-one electrolyte, a potential is positive or the point of zero charge, meaning we have a net positive charge on the interface and we have an absorbing anion, let's say sodium iodide. So now things look a little bit more complex. You might recall that the process of absorption, implied that you displace solvent molecules, in this case water, and the adsorbate also loses part of its solvation sphere. The net result is that the absorbing species is in intimate contact with the electrode surface right there. So you can see it there, you can see it there, you can see it there. And so now, if we draw a plane through the center of those species, we have the IHP, or the inner Helmholtz plane. We still have the outer Helmholtz plane and we still have the diffuse double layer, but now we have a distinct layering in this case of specifically adsorb, the counterbalancing, and then also screening out here. What do the potential profiles look like? Well, it can be rather perverse. So in the case of strongly adsorbing, you can actually overcompensate. And so even though in principle you're applying a positive potential, you overcompensate, so the effective charge on the electrode is negative. And so imagine this situation, right? You apply, I don't know, let's say 0.3 volts, your electrode thinks it's minus 0.2. Unless you know that, you're not going to make any reasonable assessment of what your system is undergoing. Then you have, again, a linear drop and then exponential into solution. So people in the asking why is it linear in the outer Helmholtz plane, in essence, you can think of it as a potential drop across two different layers of charge, okay? And so that's what basically linear, think of it as two charges across a dielectric would be the solvent. There's also the term potential zero free charge. And so what that means, you can have a point of zero charge where you still have some charges at the surface. These are they're compensated. Potential zero free charge basically means that you literally have no charges on free charges on the surface. There's also the potential of maximum entropy, but these are definitions that get a little bit too much, in the weeds. And so if you understand the concept of potential zero charge, that's enough for the time being. Okay, we can discuss that further if people want. Now, so here we have this very unusual situation of the electrode experiencing a potential that's counter to the one we're applying. And that is prevalent when you have specific adsorption, very strong specific adsorption. So for example, I chose sodium iodide or potassium iodide. That's a very well-known case on a mercury surface at around 0.2, 0.3 volts. The surface is basically so overcompensated with negative charges that the surface charge is negative as opposed to positive. Okay. We can compare that to the case of non-adsorbing in blue here. So in the non-adsorbing, it's blue, so linear to the outer Helmholtz plane, exponential to solution. In the adsorbing case, it's still linear, whoops, but now to the outer Helmholtz plane with specific adsorption, linear again to the outer Helmholtz plane, exponential into solution. And we'll get to why exponential in a second. And so what can we use as models to explain double layer and double layer phenomena? So the first model was a Helmholtz model of the double layer, which is a simple capacitor analogy. So basically, Helmholtz assumed that there was a rigid arrangement of ions. So for example, if you have negative charges here, you have the accompanying, whoops, oh, come on. Oh, God. Oh, Can people see the slides? Michael or somebody from IT here if I need some help because I got thrown off. No. We are having some technical difficulties here, folks. I don't know. I got a phone. And we are back live, folks. Sorry. I got a call on my iPhone that was connected to my iPad and it threw everything off. Just give me one quick second. Is anything we're good or? There you go. There you go. Thank you. So we're back. Sorry about the brief interruption there. So the Helmholtz model of the double layer. So this is a simple model, as I mentioned. You have a negative surface charge, and then screening of the charge on the other side. Literally a double layer. And so, if you look at, the capacitance is basically the change in surface charge with voltage. And the charge is basically the dielectric, permittivity, distance, and the applied voltage. And so the capacitance, if you take partial sigma, partial V, if this is sigma, it gives you epsilon 0 divided by D. Meaning this is not dependent on potential nor concentration. Okay. All it varies, you have a linear drop from the surface to where the ions are, and this in essence explains why in the models that we just described there's a linear drop across the two layers of charge. However, if you look at the dependence of the capacitance as a function of potential, is completely independent, as you can see from this relationship, right? I mean, if the capacitance is partial sigma, partial V, and this is sigma, right? When you take the partial with respect to V, you end up with epsilon, the dielectric permittivity of free space, and D. So there is no dependency on neither the applied potential or the concentration of electrolyte. Okay. It's a nice start, but obviously not correct. If we go to the next evolution, this is a so-called Gouy-Chapman model, or the model of the diffuse double layer. And this is a little bit more involved, so let's go through this a little bit more slowly. It says an excess charge on the surface will give rise to an electric field, and this field attracts and repels ions. No surprise there. And so the electrostatic interactions are kind of balanced by random thermal motions, basically Brownian motions in solution, and these motions give rise to a diffuse layer of charge, and this is why it's called the diffuse double layer. And then you reach an equilibrium, which, so basically what you have is the presence of the electrostatic field from the interface, the ions in solution. At some point, you're at an equilibrium, and that establishes a profile, which would basically be exponential, as we'll see in a second. And so when you reach that equilibrium, it can be represented by a Boltzmann type distribution. And so you have the concentration of species I at position X. This is the bulk density or bulk concentration, exponential of Z, which is the charge, phi, which is the potential, over KT, a simple Boltzmann type distribution. Now we can combine this with Poisson's equation to get a Poisson-Boltzmann distribution that relates the second derivative of the field with respect to position as E, the electron charge, permittivity, and dielectric, and then the sum of the various species and their charges, and then the exponential of charge potential over KT. Where does this take us? If you basically plug into the Poisson-Boltzmann expression, you get this sort of ugly-looking hyperbolic tangent that says hyperbolic tangent of ZE phi over 4KT divided by the hyperbolic tangent of ZE phi 0, right, equals e to the minus kappa x. So phi is the effective field, phi 0 is the one that you apply. And so it tells you that the decay of that field is an exponential with a decay length, that is kappa times x. Because exponentials have to be dimensionless. If x, let's say, is dimensions of distance, then kappa better be 1 over distance or reciprocal. Now, for small arguments of a hyperbolic tangent, tangent of h of x for small x equals x. And what that means then is that phi over phi 0 simplifies to this amazingly convenient expression. That is, the potential decays exponentially away from the electrode surface with the decay constant kappa, which is termed the Debye length or the characteristic thickness. Notice that it has units of 1 over length, just to make sure that the exponent is dimensionless. For water at 25 degrees C, kappa can be guesstimated as a constant charge and then the square root of the concentration or the square root of the ionic strength. And so you have kappa equals this collection here. If you look at what the potential profile looks like, you can go from small phi zeros to very large phi zeros, meaning the applied potential, as we mentioned earlier. Remember, phi 0 is the applied potential. Phi is the potential at some distance x from the electrode surface. For small arguments, say 10 millivolts, you have sort of the limiting form, which is exponential, and you have this exponential tail coming out into solution. As you get further and further and further away from the inner from that condition, so if you go to 100 millivolts, or in this case 1,000 millivolts, the decay is incredibly sharp here. Why is that? Because when you put that much charge on the electrode surface, you're really compressing, you're bringing a lot of ions to that surface. The capacitance is going through the roof. The decay is extremely sharp. What are the consequences of this? Does it explain the dependencies? It's clearly dependent on potential because we see it right here, right? The decay of that potential is enormously dependent on the potential. Does it depend on ionic strength? It's right here. And so the scaling, okay, it's useful to have a couple numbers, as we'll see in a second. The scaling, at 0.1 molar ionic strength, your Debye length is about 10 angstroms. And that's a really convenient number, 9.6 or something, but let's say 10 angstrom. That's a really convenient number to how far, what's the extension of the double layer in this context. And so the Gouy-Chapman model is something like this, where you have a fixed charge at the electrode surface, right? Because of Gauss's law, you cannot sustain internal electric fields in a metal. And so you have now a diffuse layer of charge away from the interface, which is exponential because of the distribution that we just saw. Basically, well, from the Poisson-Boltzmann, that's where the exponential comes in. Okay. And so the characteristic thickness, or the thickness of the Debye length, as I mentioned, at 0.1 molar is about 10 angstroms, 9.6. And so you can do the scaling immediately. If I go an order of magnitude higher, it should be the square root of 9.6. Let's call it 3. If I go an order of magnitude lower, I go to 30, etc., etc. And so this provides you a very convenient way of knowing how far into solution your double layer is penetrating. Now, one can also determine the charge density on the metal. And so this is, KT, dielectric, permittivity, density, and then this hyperbolic sign again on the applied potential, this phi 0. And from this, one can calculate the diffuse double layer capacity, a constant, the charge on the ion, again, ionic strength, in this species. If we do that, what do we get? Do we get something that looks like this? At low ionic strength, this might be, let's call it that 30 or 40. As you increase the ionic strength, this thing really starts shooting up. Let's say at 1 molar and at 50 millivolts from 0.0 charge, we're talking about capacitances of 500 microfarads per square centimeter. If you ever seen a 500 microfarad capacitor, you would stay away from it because it can kill you. So obviously something here is not quite right. What is that? So the double layer capacity for reasonable electrodes of the order of maybe 20 to 30 microfarads per square centimeter, somewhere in this regime, which applies at relatively low ionic strength. What's happening here is that the assumption in the Gouy-Chapman model is that it assumes that ions are point charges. When you go to a very high ionic strength and a polarization is far removed from the point of zero charge, those species can get arbitrarily close to the electrode surface, less than the atomic dimensions, because there's no constraint. This is just math, right? And so because of that limitation in the model, you get unphysically large values of capacitance due to the fact that you're trying, conceptually to bring an ion to, let's say, within 0.1 angstrom from the surface, which you cannot do because the ion is bigger than that. And the resulting charge density gives rise to these enormously large values of the interfacial capacitance. So this is a good start, but not quite there yet. So what do we do next? In essence, we combine both the Helmholtz model and the Gouy-Chapman model. And so in this case, what we will have is two layers of charge, one close to the electrode surface as described by Helmholtz, another diffuse double layer as described by Gouy-Chapman. So now we have, in essence, two capacitors in series, right? This is the, let's say, Helmholtz. This is Gouy-Chapman. But capacitances add as reciprocals, right? And so now we have to figure out where or under what conditions does one dominate over the other. So remember, for the diffuse double layer, when we are at high ionic strength and a potential is far removed from the point of zero charge, the double layer capacitance, as we saw here, is just shooting through the roof, right? Just ginormously big values. Because we're adding reciprocals under those conditions, because it's so large, then the Helmholtz layer or contribution will be dominant. So dominant at high ionic strength, a potential far from the point of zero charge. Why? Because under those conditions, the Gouy-Chapman or diffuse double layer capacitance is enormously large. On the other hand, if you look to go to low ionic strength, a potential is close to the point of zero charge, then the Helmholtz capacitance, the diffuse double layer capacitance is low, small relative to the Helmholtz, and thus it will dominate. And so you see, because of reciprocals, the double layer capacitance, the Helmholtz will be dominant at high ionic strength, the diffuse double layer dominant at low ionic strength. And so this is basically what we just saw before. We have the Helmholtz capacitor, diffuse double layer capacitor, basically combining to give it the overall double layer capacitance. And so we have, if this is the applied potential, again, we have a linear drop. This would be the outer Helmholtz plane, and then the diffuse double layer. The combination of the inner Helmholtz plane and the outer Helmholtz planes is often referred to as a compact double layer. Whereas the extended region after that, basically diffuse double layer. And so those are the two components of the double layer structure. We can visualize a little bit more. Again, we have 1 over the double layer capacitance, 1 over the Helmholtz, 1 over the diffuse double layer. As we mentioned, at high electrolyte concentration and potentials far removed from the point of zero charge, the diffuse double layer capacitance is much, much bigger than Helmholtz, and therefore, if this is a big number, then the double layer capacitance will be dictated by the Helmholtz layer. At low electrolyte concentrations or low ionic strength, and at potentials close to the point of zero charge, the Helmholtz capacitance is bigger than the diffuse, and so therefore, double layer will be controlled by the diffuse. And so we can, in some sense, schematically think of it this way. Remember that the Helmholtz capacitance was constant, right? That was one of the issues with it. So we have the Helmholtz capacitance, essentially a flat line here, you can see, right? It will be completely flat. And that's modulated by the diffuse double layer, which is important at low electrolyte concentrations and potentials close to the point of zero charge. And so the overall behavior is a sum of the constant and this dip here, which gives rise to what we saw before, which is basically something like that. So this is dominated by Helmholtz. This is dominated by diffuse. Do we see any evidence of that? And the answer is yes, in the double layer capacitance of mercury surfaces. Now we need one more modification, and this is the modification that was put forth by Graham. So in the Graham model, we also include an inner Helmholtz plane for a Dörr species. And so in this case, we have the inner Helmholtz plane, the outer Helmholtz plane, and the diffuse double layer. And so we have potential profiles, as we've seen before, that can actually overcompensate. If we look at the double layer capacitance, this is actually for mercury. So you can see, you know, if we play a little bit fast and loose, we can think of this as really being, this basically represents the sum of that plus that. And so you have, I mean, just being a little liberal here, something like that. And so it captures really a lot of the essence of what we know to be the case from experimental observation. One last model. This is the model of Bockris, John Bockris, who was an interesting character initially from Imperial College, then at Australia, then at Penn, then at Texas A&M. So he also added a modification where you have a layer of solvent at the electrode surface. That layer of solvent is displaced if you have specifically adsorbed ions, or not if you have non-specifically adsorbed ions. And so it modifies the interface by having something that looks like this, where you have solvated ions, unsolvated negative if they're specifically adsorbed, and basically water dipoles or water molecules. And so this looks a little bit more, it almost looks like a beehive. If you look closely, you'll notice that the arrows of the solvent, see if we can, you can see that they're much highly polarized here than outer here, which are a little bit more random. And that's because as the ions screen the electric field strength is weaker as you move out. In essence, you see the decay of the divide length. Okay. A couple of things, that to keep in mind. If you have electrical, an electrochemical phenomenon, and for example, you see a displacement of, let's say, a formal potential with ionic strength, and it scales as the square root of the ionic strength, you can bet good money that it's electrostatic. Why is that? Because at the bi length, the scaling is 1 over the square of the ionic strength, or 1 of the square is basically square root of the ionic strength because it's 1 over the square. And so any scaling that goes as 1 over the square of the ionic strength, you can be quite sure that is electrostatic in nature. And that provides a very simple way of identifying when you have electrostatic effects in your measurements, as opposed to might be other effects experimentally. A couple of things on how you might do some of the measurements here. And so one of the easiest aspects to measure charge or capacitance is to do a potential step. And so you impose a potential step at some specified time. So here is your potential step. That gives rise to a transient current that will look like that, and we'll see later on why it has that shape. And so if you integrate the charge, or integrate the current, you get the charge. Remember that Q equals the integral of I dt. And so if you measure the charge will have this characteristic profile. And so you can then, with time, measure the charge. So Q double layer equals Faraday's constant, and then the cation surface excess, anion surface excess. It's quick and dirty, but it's dirty, meaning that it's incredibly sensitive to impurities. And if you recall way back when we were talking about charges, if one of those impurities happens to have a bit of a Faradaic process, that really has a huge effect on your measured capacitance. One can also employ linear sweep or cyclic voltammetry. The idea is to scan the potential over a regime that there's no Faradaic process. So there are no redox processes involved, meaning it is all double layer charging. If you increase the sweep rate, so here the sweep rate, so VA is smaller than VB is smaller than VC, you can see that the double layer capacitance of the current here scales linearly with sweep rate. And remember, because the double layer current is a double layer capacitance times dV/dt, this is nothing more than the sweep rate, which would be the linear sweep in a voltammetric profile by cyclic voltammetry. So this ends the first set of lectures. Again, we're at the top of the hour. Let's take 5 minutes. And also, if I could have one of our friends in the chemistry AV help me load up the next series of lectures. These are the ones that I sent last night to all of you. So we'll see you in about 5 minutes, I hope. Okay, folks. So up until this point, everything that we have discussed is really those the fundamental concepts of electrochemistry. And so now based on the comments here, can everybody see my slides and hear me? And the answer is yes. Okay. Okay, we're good. Okay, so let's continue. So up until this point, we've been talking really conceptual stuff, meaning theory of electron transfer, theory of absorption, charge transfer kinetics, etc. So now we are turning into specifics of techniques. So from now until the end, we're going to be talking about specific techniques of electrochemistry, how we carry out those measurements, how do we interpret the data. And we start with methods based on hydrodynamic transport, which is rotating disk voltammetry or voltammetry in general. And so what are the constraints in voltammetry? Give me just a quick second here. So in voltammetry, this is going to be controlled by hydrodynamic transport. The response, as we'll see in a second, is going to be steady state. This is not transient. And so when we develop potential current relationships, they will be reciprocal, meaning if in an electrochemical system, if you tell me the potential, I can tell you the current and vice versa. So what does this entail? So in these experiments, you either stir the solution or rotate the electrode. What does that give rise to? And so we need to consider what the transport is in the region close to the electrode surface. And by that, I mean, what are the transport profiles as you get closer to the electrode surface? Far from the electrode surface, you're going to have turbulent flow, meaning all hell breaks loose. You have no idea. I mean, you have all types of, things going everywhere. If you ever, for example, for those of you who do experiments and you have like a stir bar, you generate, these vortices and, cavitation, all kinds of nonsense. As you get closer to the electrode surface, then the flow begins to change dramatically and you get laminar flow. And in particular, we will assume that we have perfect laminar flow. What that means is that you have sheets of solvent basically moving past each other. And that's what's being conveyed here by these lines. So this basically represents sheets of solvent that are moving past each other. One assumes that this is very fast transport. Beyond that, then very close to the electrode surface, you have what's called a Nernst layer or the Nernst layer thickness, given the letter delta. This is a layer of stagnant liquid at the surface, stationary. It's not moving. What does that mean? It's the only region that will be able to sustain a concentration gradient. In the region of laminar flow, we assume perfect laminar flow, meaning things are getting mixed so fast that there's no concentration gradient. Beyond that, in the region of turbulent flow, we don't care, basically. We know it's there and we don't care. What we do care is what happens in the Nernst layer, because that's where concentration gradients will be able to be sustained. The Nernst layer is also sometimes called the diffusion layer thickness, not to be confused with the diffuse double layer. It's a diffusion layer. In terms of magnitude, we're talking here microns. Remember, the diffuse double layer is nanometers. So we're talking 1,000 times bigger. So try not to confuse these two phenomena or these two length scales. And so here we have a potential axis. We have a potentials A, B, C, and D, and we have a redox process that has a potential in between B and C. And so what we're plotting at the bottom is the concentration of ox as a function of distance. So at potential A, we are so far removed from anywhere close to ox red that nothing is getting oxidized or reduced. So if we look at the concentration profile, it's absolutely flat out, right? And this is the bulk concentration. When we get to potential B, we're beginning to get close enough so that we turn over from the ox to red, meaning that the surface concentration of ox is going to be below the bulk concentration. And for the time being, we'll assume it's linear. Away from delta, this is basically bulk. Remember, you have perfect laminar flow here. It cannot sustain a concentration gradient. At C, we're really cooking. At D, we're well beyond ox red. So what happens at D? The surface concentration of ox goes to 0. All right, so CS ox 0. That's referred to as quote unquote complete concentration polarization. Right? It cannot go no lower than that. You cannot have a negative concentration. So now the question is, how do we use this framework to obtain an expression that will be useful from an experimental standpoint? And this is where we start with Fick's laws of diffusion. So Fick's first law, actually second law, tells you that the current equals the number of electron transfer, Faraday constant, or the electron diffusion coefficient, and partial C, partial X at X equals 0, meaning what is a concentration gradient at the interface? That provides a driving force, or the flux, that in turn controls the current. We will start with the condition that we have only ox in solution. There's no red, okay? And so we have current equals number of electrons, Faraday constant, area, all of these are constants, right? And then partial concentration of ox at the surface as a function of distance and time, the gradient of that at the surface. So this is basically the gradient or the slope. If we go back to here, if we know the value here because that's the bulk, and we know the concentration here at some value, so if I take that difference and divide by delta, that's close enough to the slope. And that's what we do here. C bulk minus C surface divided by delta. That's a proxy for the derivative or the gradient. And so when we do that, since we have ox, we're talking about cathodic or reducing current. So we have NFA D0 divided by delta. We basically lump all of these parameters and conveniently call it K0. And so if we do that, we have that the current is K0 multiplied by the difference between bulk concentration and surface concentration. When the surface concentrations go to zero, that is when you have complete concentration polarization, right? If this goes to zero, whoops, then clearly the current is at the maximum because you're not subtracting anything here. And so the limiting current, I limiting cathodic, is basically K0 times the bulk concentration. And so since we now have solved for that one, we can express that the current will be the limiting concentration, the limiting current minus K0 times the surface concentration. We can then solve for the surface concentration of ox, I limiting minus I over K0. Now for red, whose concentration is controlled by ox, right? That's because there is no red in solution. So the flux of red is basically the negative of the flux of ox because of conservation of mass. And so before, so here we have, before we have NFA D0, the gradient of the surface concentration of ox, we put a negative sign here, and just to be safe, we use the diffusion coefficient of red as opposed to ox, but basically it's the same thing. So now we have the current, another current, same idea, NFA dr over delta, bulk concentration, surface concentration. Right? But what's the bulk concentration of red? That's basically zero. Right? And so we get I equals NFA D delta CR. Right? Because this negative cancels that negative. And so now we have this expression for the current. So now we can solve for the surface concentration of red. It's I over KR. If we were to plot the current, we would end up with a profile that looks something like that, where we have, as we get, again, using the same potential that we had before, zero current, we come up and eventually reach a limiting current right around here, which is basically when we reach complete concentration polarization, that is when the surface concentration of ox goes to zero. And so if we look at reversible reactions, remember our definition of reversible, meaning the system is always at equilibrium with the applied potential. This is nothing more than the Nernst equation, right? E equals 0.059 over n log ratio of ox and red. But we know, I mean, we've already figured out what those are, right? This was CR, and this was CO. So we substitute for those. E equals 0.059 log I limiting cathodic minus I over K0, I over KR. If we collect terms, this ratio KR, K0, etc., we will call this E1/2. So we get that E equals E1/2 plus 0.5 I over N log I leading minus I over I, this expression. If you plot that, you get what we saw before. A profile. So at low potentials here, very little current, as we increase the driving force and eventually getting to a limiting current, that's limited by basically mass transport of aux. E1/2 is basically the potential at half the limiting current, somewhere out here. And E1/2 is a characteristic potential of a specific redox couple. It's independent of concentration. It's independent of anything else. It's inherent to the system. So it's a very nice way of characterizing a redox system, right? And so you can see that when the current is half the limiting current, right? So if this is 1 and this is 1/2 and this is 1/2, 1 minus 1/2 divided by 1/2 is 1, log of 1 is 0. This drops to E equals E1/2. And that's basically what that is. For a reversible system, if you make a plot of E1/2 versus the current term, this will be linear with a slope of 59 millivolts. Why? Because this is Nernst. And an intercept that's E1/2. Now, we can do the same analysis in the case of having only red in solution, right? And we'll cut to the chase. In that case, you get E equals E1/2, 0.59 log minus I minus I limiting. And again, at half the limiting current, you get the same E1/2, except that now we're looking at an oxidative or anodic current. And then, of course, you know what's coming next is basically putting both together. And so this gives you an expression for the voltammetric profile for aux going to red, where in this case, you have the anodic current, the cathodic current. For irreversible reactions, again, aux only present, let's assume that the reaction is totally irreversible, meaning we don't have to take into account the reverse process. If we do that, we get an expression as shown in here. How is this different? Well, you notice our good friend alpha. Na is the number of electron transfer in the redetermining step, and we get our friendly Ks, meaning we have to bring the concepts of charge transfer kinetics into the expression. So this basically modifies or displaces the potential profile. Notice that all of this is basically prior to the current function here. So what does this mean? It means that for an irreversible system, the effective E1/2, and by E1/2, remember, that's the potential at half the limiting current. And because you have a process that's irreversible, it will be displaced on the potential axis in the negative direction. Why? Because you need a higher driving force to reach the same current. So if this is the profile for a reversible process, the irreversible one will be displaced on the potential axis. In addition, the steepness will be shallower for the irreversible process. If we do the same thing we did before, that is make a plot of the potential versus the current function, this will be linear, but now with a slope of 59 over alpha NA millivolts. So if we assume that NA equals 1, and assuming that alpha is 0.5, now we have a slope of 118 millivolts as opposed to 59 millivolts. And so if we look at irreversible ways, again, only ox present in solution. So this would be, if we go, whoops, let's say A, B, and C, KSA bigger than KSB bigger than KC. Two things you see. One, the profile is displaced on the potential axis to more negative values. And the shapes, the profile are shallower. The slope is steepest in A, less so in B, less so in C. Where does this come from? You might recall when we were plotting, this was eta and current, remember for different Ks, where Ks was decreasing in this direction, that's where those profiles come from. If we have both ox and red in solution, for a reversible case, basically this cuts, if we have equal concentrations of ox and red, it'll cut through zero, at the potential will be the E1/2. As the reaction gets increasingly more irreversible, you may actually have a splitting of the cathodic or the reduction and the oxidation, and you might think that you have two discrete redox processes, and you don't. And so you have to be very sensitive to what the profiles look like and what they're telling you. Now, very often, one has reactions that involve generation or consumption of protons or hydroxide, and that then modifies the expression that we have. So how does it do that? And so this is what we had before, with C red and C ox. This was 1 over KR, 1 limited minus I over K. We have an extra term, 0.059 over N log concentration of protons. Or if you want to change that, minus 0.059 M, the number of protons transferred, over N pH. Which means what? If you have a system that consumes or generates protons or conversely hydroxides, the E1/2 will be a function of pH. And if you measure the displacement of the E1/2 with pH, you can basically get M, the number of protons involved in that process. So mechanistically, it is enormously valuable because it's a simple measurement. Just measure the displacement of that voltammetric profile as a function of pH. And for those of you who are more, let's say, on the inorganic chemistry community, and you might say, what are we, chopped liver? What about ligand exchange? The same thing, happens here. So if you have a system, let's say, ox with, M moles of ligands, and you reduce it and it gives you R, and you generate M moles of ligand, the same thing will happen. That is, the E1/2 will be displaced as a function of ligand concentration, but there's a constraint here, and that is that you want to make sure that the concentration of ligand is bigger than the concentration of your complex, so that you're not limited by the concentration of this guy in the displacement of the voltammetric profile. And so this is a sort of introduction to the basic concepts of voltammetry overall. Now, one of the issues in voltammetry, and this goes back to our sleight of hand, when we said K0 equals NFAD0 delta, we basically lumped this into K because it was convenient, but we really have no idea what delta is, right? And so there's a imprecision, so to speak, in this analysis. And so how do we compensate for that? Meaning, how can we make voltammetric techniques more quantifiable than just simply qualitative, which is what these profiles will tell you. And this is where rotating this electrode voltammetry comes in, right? And so the top here shows you a typical rotating disc. If you're going to buy one, buy them from Pine Instruments. They are the best, period. No substitutes. And so in a rotating disc electrode system, you rotate the electrode and you have these profiles of solution coming to and radially being pushed away from the electrode surface. That controls the flux to the electrode surface. And as you see here, as you change the frequency from 5 to 12 to 25, the current increases, and as we'll see in a second, the current will scale as the square root of the rate of rotation. So how do we understand transport and put this in a more quantifiable fashion? So here we have a general transport equation. So dCox dt, meaning the rate of change of the concentration of flux with time, will be given by the diffusion coefficient, variations in x, y, and z, variations in velocity with x, y, and z. So this is concentration gradient, this is velocity gradient. We can also express this in radial coordinates, but we won't get into that here. After a little bit of, as I like to say, tedious algebra, etc., you can actually derive this equation that tells you that the current is this factor 0.62, number of electrons, Faraday constant, area, diffusion coefficient to the 2/3 power. Notice that. Kinematic viscosity to the -1/6 power, rotation rate to the 1/2 power, C bulk minus CS. If, as we've done before, if we let this go to 0, we get the limiting current, which is 0.62 NFAD to the 2/3 CB. And this is known as the Levitch equation. It's in this book called Physicochemical Hydrodynamics. As I mentioned in previous occasions, if you have problems falling asleep, this is your ticket, right? It is dense, but it is extraordinarily rigorous. Here, IL is the limiting current, the diffusion coefficient. Nu is a kinematic viscosity, which is viscosity divided by density. For water at around 20 degrees C, it's about 0.01. And omega is the rotational frequency in radians per second, okay? If you want to use hertz, you have to do the appropriate conversion. Why is this any better than what we had before? So you might recall that before, when we were talking about limiting current, we said that we have K0 multiplied by the bulk concentration of Ox. That was the limiting current, right? Because we had that the current was K0 C bulk minus C surface. When the surface concentration goes to 0, we have complete concentration polarization, we get the limiting current. However, K had this little delta, which was the Nernst diffusion layer thickness, that we basically swept under the rug because we did not know what the hell that was. But now we do. Why is that? If we go back, right, this expression is no different than K multiplied by C0 bulk. So this entire term, that's K, right? And because of that, now we can actually solve for delta. And so it tells you that delta 1.61, again, d to the 1/3, nu to the minus 1/6, omega to the 1/2. What do we notice here? The magnitude of delta scales as 1 over the rotation frequency. Delta controls the gradient, right? The smaller delta gets, the steeper the profile, the higher the current. And so, because delta decreases with increasing frequency, the current will increase with increasing rotation frequency, and it will increase as basically the square root of the rate of rotation, which is what we saw before. In addition, and this will be relevant later on, you can calculate the transit time. How long does it take to move away from the electrode surface? And that's basically given by delta squared divided by 2d, where d is the diffusion coefficient. So it's useful to consider some numbers so you get the scaling in the right ballpark. As we mentioned previously, we're using simple math, 9 times 10 to the minus 6 centimeters squared per second, even though here we're taking the cube root of that. Kinematic viscosity, 0.01 centimeters squared per second. Notice that this has units of diffusion coefficient. Typical omega, let's say 1,000 RPM, it's about 100 radians per second. Under these conditions, delta, the Nernst diffusion layer thickness, is about 15 microns, 15 microns. Remember, the extension of the diffuse double layer is in nanometers, maybe tens of nanometers. So we're talking about 1,000 times bigger. On this scale, the diffuse double layer is basically smack against the electrode surface. If you go to 10,000 RPM, which is really cooking, your Nernst diffusion layer thickness is about 5 microns. So this gives you sort of a sense of magnitude in these experiments. Now, in the Levitch equation, we know or control essentially all the parameters except D. And so the Levitch equation is very often used for really precise measurements of diffusion coefficients. You can get it from the slope of a current versus square root of rotation rate from that plot. In addition, because the limiting current is proportional to the square root of the rate of rotation, we can control the rate of the reaction by controlling the rate of rotation. This means that you decouple potential and transport. It also means that you can make measurements at short experimental times by going to high frequency, or long experimental times by going to low frequencies. So you have an enormous level of control under extremely well-defined conditions of transport as well as potential. In addition, right, we have to scan the potential slowly to maintain a steady state. Remember, this is a steady state method. It's not a transient method. If I have a profile, right, like that, and I hold the potential here, the current ain't moving, it's staying there. If I hold it there, it's staying there. If I'm then scanning the potential, it means to be able to state that I have a steady state response, I have to ensure that I use a low sweep rate, typically of the order of 10 millivolts per second. And so if we make a plot of current versus square root of rotation, we should see a straight line that goes to the origin. And the expression that describes this is essentially identical to what we derived before. Mathematically, they're identical as they have to be. The only difference is E1/2, instead of having the square root of diffusion coefficients, is the 2/3 power. Given that DO and DR are almost always the same, this is basically insignificant. And so E1/2 will be just like we saw before. Now, so what happens when you have complications due to slow kinetics? That is, kinetic limitations, irreversibility. If we do a Levitch plot, that is a current versus omega to the 1/2, this is the Levitch line. If we see points deviating away from that line, especially as you increase the rate of rotation, we can suspect slow kinetics. Why is that? What is the rate of rotation doing? It's controlling the flux to the electrode surface. If the electrokinetics are fast enough, then it can turn over aux at whatever rate you're giving it. On the other hand, if the flux is higher than the kinetics can accommodate, what you'll see is a deviation from the Levitch line, and eventually it will become independent of rotation, meaning you have reached the kinetic limit. It doesn't matter how much you're feeding it, it's not going to eat any faster. And so, how do we analyze for those cases? As we've done in the past, assume that the reaction is completely irreversible. That is, the reverse process is, for all intent and purpose, negligible. Remember, this was from previous discussion. And so we have K equals Ks, E alpha NFA, da da da. This comes hopefully from yesterday's lecture and the derivation of the Butler-Fulmer. Now, we can define a kinetic current that is independent of omega. And that would be this expression. That current, in the absence of any mass transport effects, right? We want to be sure that we're not mass transport limited. We can ensure that by choosing to work in a region that we know we're kinetically and not mass transport limited. That is, if we want to figure out the kinetics, we better work in a regime where the kinetics is controlling the response. And so if we're at the foot of the way where it starts, we know that we are not mass transport limited, but rather limited by the kinetics of the electrode reaction, and therefore we can call that the kinetic current. If we go back to our previous, let's say, go back to here, right, to this view here. So we again have current as a function of the rate of square root of the rate of rotation. This dashed black line would be the Levitch line. The red line, you can see it bends over and has a limiting value of IK. It's controlled by kinetics, not by mass transport. Right? Because we're at a potential that we know we're not mass transport limited. And so the fact that it's bending over is telling you that as we increase the flux, which is what omega does, the electrode reaction cannot keep track with the increased flux of reactant to the surface. And so then what we do to analyze this, what we do is take the reciprocal of the current. That will be equal to 1 over the kinetic current plus 1 over the limiting current. So we have 1 over I, 1 kinetic, and then this expression. A plot of 1 over I versus 1 over omega to the 1/2 is known as a Kotecki-Levitch plot. And this will be linear. And if we extrapolate to 1 omega going to 0, meaning infinite rate of rotation, the intercept will be 1 over k. If we do this at various potentials, we can determine the kinetic parameters Ks and alpha. That will look something like this. 1 over I versus 1 over omega to the 1/2. These, that one, let's see, that one, and that one are kinetic currents at those potentials. What about E3, the blue line here? It goes through the origin, right? If the intercept is 1 over IK, then that means that for E3, we are not kinetically controlled. In essence, it's infinitely fast. And so that tells us that we violated our premise, right? So this is a voltammetric way. If this is E1, this is E2, this is E3. And so we're no longer kinetically limited, but rather mass transport limited, right? And that's why it goes through the origin. And so this is an expression that you can apply. It gets a little bit involved, but basically it's just, it's just, keeping track of all of these parameters. And so this plot will be linear for a given over potential. And from that and the intercepts, we can backtrack value of Ks as well as alpha. And so this is the Kotecki-Levitch analysis. It's used a lot, in things like oxygen reduction reaction, because these are kinetically slow. And it's the best way to obtain really reliable information, because the intercept is really, you're putting a lot of points in these profiles, right? You might have 8 or 10 different rates of rotation. And so the intercept is basically a linear fit to those points. So it's very reliable. And so it gives rise to very, very high quality data simply by doing the measurements at a range of rates of rotation. And so, and the summary here is that one can look at the Levitch plot, I versus omega to the 1/2. If it's linear, we know the system is reversible. When it deviates, we know we have kinetic complications. In those cases where we have kinetic control, then we use Kutetchky-Levitch. So here we have, it's actually, these are real data. So these points are basically those points plotted in a Kutetchky-Levitch analysis. And from that, from this IK, we can actually get Ks for this process. Now, an alternative way is to look at how the shape of the voltammogram changes with omega. And what do we mean by that? If we go back here, when we change omega, our system, at small omega, the system is perfectly happy, meaning the rate at which you are providing reactant to that surface is slow enough that the kinetics can accommodate that, meaning we're mass transport limited, not kinetically limited. As we increase the rate of mass transport, now we start to compete with the kinetics, and at some point, the mass transport is faster than the kinetics, and so we become not mass transport limited, but rather kinetically limited. Now, the question then is can we analyze the form of these current potential profiles so as to qualitatively see what differences there might be? And this is what we mean here. That is how the shape of the voltammogram changes with omega. But we have a complication, right? Because the current scales with omega to the 1/2. And so if we want to understand the change in the shape of the voltammetric profile, what we need to do is normalize the current to the square root of the rate of rotation. And so these are so-called normalized current profiles, where we plot I divided by omega to the 1/2 versus potential for different values of omega. And as presented here, from left to right, we go into increasingly higher values of omega. As we saw previously, when we're talking about sort of the generic theory of voltammetry, a reversible case, the E1/2 will be, let's say, here, and the profile is very steep. As we get to increasingly less kinetically facile processes, put in another word, as Ks gets smaller, we see a shift in the E1/2, and the profile gets much shallower. In the extreme case of the black, we see a dramatic shift in E1/2 and much shallower. In general, Ks controls the position of E1/2, alpha controls the shape of the profile. Now, we can also get some idea as to whether we are activation versus mass transport controlled by looking at the ratio of K forward delta over diffusion coefficient. If Kf over times delta over D0 is bigger than 1, you have mass transport control. Why is that? Because it tells you this Kf times delta, right? It tells you the rate and the Nernst diffusion layer thickness, It tells you the rate at which you're converting stuff. If it's bigger than D0, you're mass transport control, not kinetically controlled. If, on the other hand, the reverse is true, then for the same, sort of the reverse arguments, you're going to be kinetically controlled. So simple ratios here. And remember, this this you can guesstimate quite well. And so you can basically get a sense for KF by just doing this type of experiments. Okay. In my view, the real advantage, and I'm a big fan of rotating these experiments. One of the biggest advantages of rotating this voltammetry is that the math is very rigorous. Because you decouple the potential from the transport, that gives you a lot of leeway in terms of experimental parameters. Also, because you're sweeping the potential slowly, then resistance effects are dramatically mitigated. And so even though in the community at large, for some reason, people love cyclic voltammetry and the ducks, floating around, as we'll see later on, to me, cyclic voltammetry is very good for identifying mechanisms, rotating this electrovoltammetry much better to quantifying what those kinetics are. With that in mind, we begin very briefly here in context. How do we use rotating this voltammetry to understand mechanisms of electrode reactions other than simple ox plus electron going to red, meaning generically so-called coupled chemical reactions, meaning how does a voltammetric profile get modified or affected by having reactions that are coupled to the electron transfer event. In this context, we use a combination of letters C and E. C refers to a chemical step. E refers to an electron transfer step. And the order makes a difference. And so we can talk about a CE process, meaning that there's a chemical step that precedes the electron transfer. And so CE is generically referred to as prekinetics. More often than not, you have a pre-equilibration that gives rise to the generation of your redox active species, meaning X is what you put in the beaker, Ox is what's redox active. For example, you might have a metal complex that requires the loss of one ligand to be redox active. That equilibrium will dictate how much Ox you have. That's a pre-equilibrium, and thus prekinetics. If you have prekinetics, obviously you're going to have postkinetics. And so this is a reaction that follows the electron transfer. Very often, it's a decomposition, not what you want. And so you have Ox plus any electron goes to red, red goes to Z. Z may or may not be redox active, and so you can have different variants of that. And so, whereas in a prekinetics, the concentration of Ox is affected, here the concentration of red is affected because it follows the electron transfer event. One can have catalytic processes. So it's called EC-cat because you have Ox plus any electron goes to red. Red reacts with substrate to give you product and regenerate Ox. And that's where the catalytic process comes in. And then ECE, meaning two electron transfers that are separated by a chemical reaction. And there's two variants. So you have Ox plus electron going to red. Red reacts to give you Y, and Y is redox active. So it depends on whether the two redox potentials, E0'1 versus E0'2, whether one is positive or negative of the other. In one case, the second, if we're varying the potential that way, the second process is easier than the first. in this one, the second process is more difficult than the first, and that's going to have enormous impact in terms of what we observe experimentally. It is 5 minutes before the hour. My voice is giving up, so I will stop here. If there's any questions, ask them now. We have a few minutes before we call it a day. Thanks for your attention, folks. What are the materials you referred to? I don't understand the question. Saravan Kumar. I'm killing your pronunciation of your name, but I don't understand what the question is. If you can elaborate, I can try to answer it. Well, I assume that there's no further questions, so we'll see you tomorrow, folks. If you have any questions, you can send me an email. Bye.